So this presentation is particularly for all those who have spent their lives searching for precious or base metals and would think that exploration for silica is boring. I am here to change your mind, and mostly because you will have to rewire your thinking from thinking about a metalliferous system to a non-metalliferous one. All right. So first and foremost, what's driving the demand in development and use of renewable energy renewable energy technologies such as solar power. That is why we need silica. So I'm not a solar panel specialist, but I will be talking a lot about solar panels. So we need silica for things like solar panels. And silicon is also used in solar panels, so optical fibers, mobile phones, computer screens, flat screen monitors, all things like that. And it is also a semiconductor and therefore used as transistors. So here is a little bit of a kind of insight into, I don't think you can see my pointer. So insight into what a solar panel looks like, and the high transparency glass, which is made out of silicon, may comprise up to 97% of the solar panel's weight. So it's important. Next. I have to admit that a bit of, and while I was working on this project, a bit of injustice is being carried out towards silicon, simply because there is a real mess with the naming conventions. Silica, quartz, silicon, all of these terms are used, but what we really want to say is silicon because the other terms are minerals and we are after the element. Silicon is one of the most common elements in the Earth's crust, only preceded by oxygen. However, it's almost never found by itself, and almost always with oxygen as the silicon dioxide or in some sort of a silicate. And what's the next point I wanted to say? The term silica, I should say, is probably mostly reserved for silica sand exploration. And the quartz is probably, or high purity quartz is reserved for industries that are extracting quartz from large quartz veins. As such, quartz is what we're after. And of course, so in addition to silica being one of the most common elements in the Earth's crust, quartz itself is one of the most common minerals in the Earth's crust and can be in igneous, can be in metamorphic, can be in sedimentary rocks, and of course, of various ages, right? However, we are after high purity material. That is the only thing that is suitable for these technological applications. However, quartz in general can be used in construction, ceramics, you name it. So how do we get this high purity stuff? It is actually obtained through an extremely energy intensive refinement process, otherwise known as the carbothermic reaction. So we need lots of carbon, such as coal or wood chips or charcoal, and extremely high temperature to release silicon. So that's in general the reaction. And there are two important factors for this reaction. Oh, what's my pointer doing? So there are two important factors for this reaction. Silicon dioxide has to be pure, and this whole process in and of itself has to be has to contain as little impurities as possible, because all of that will end up going into the silicon product in the end. To reinforce the point, we know quartz can be of various colors. And what I'm trying to say is color is very easily affected by impurities. And like roughly speaking, we are after the colorless bit that is the most pure. And then we are wanting to obtain a 99.999 by weight percent silica product out of that reaction. So we want the quartz to be pure, and the silicon refined from the quartz has to be essentially ultra pure. So this places very specific requirements on the quality, origin, type, volume, as well as the resulting physical and chemical properties of the raw material that we're after. In terms of where silica or quartz is found around the world, well, probably not surprisingly, the majority of it is being explored in China. And Australia is not currently considered to be a significant producer of silicon. It's lumped into the rest of the world in this diagram, which is particularly interesting because the Cape Flattery silica sands mine is the largest silica sands mine in the world, located in far north Queensland, but doesn't make it into the cut still. But having said that, Australia is actively adopting the renewable energy and renewable energy technologies and contributes 2.4%, so considered seventh in the world in terms of uptake of solar panel installations, rooftops and solar farms. But China still leads the way, 35.6%. That means essentially every third house in China has a solar installation of sorts. So the reason for this, for these numbers is Australia largely relies on the import of already refined silicon and the import of the solar panels themselves. That is to say, like every single grain of sand from Cape Flattery is exported out. Needless to say, the cost of the silicon metal production is currently considered to be quite high. And there's a degree of variation in the produced quality of it. So in other words, as a society working towards decreasing the cost of silicon metal production and increasing the quality is something of importance. Common geological settings, and I'm I understand that I'm being very different from the presentations that we've heard, but at the same time, still going to be applying the same mineral system to mappable criteria. So briefly, the common geological settings and deposit types, along with the chemical properties and the preferred uses in the industry. But since we are after exceptional chemical and physical properties of the quartz, certain geological settings can be discarded right away simply because they're either not big enough or by sort of their geological nature, they contain too many impurities and so are not suitable for our purposes, but they could be perhaps suitable for like construction, let's say. In other words, all of this can be summarized into the Alaskite quartz, pegmatite and hydrothermal quartz, and quartz silica sands. Alaskite, in this sense, sort of in the context of this presentation, is plutonic rock composed of 75% quartz, less than 20% alkali feldspar, and trace mafic minerals. So it's essentially a silica-rich leucocratic granite. And for the purposes of this presentation and the discussion, I'll be grouping these, so the Alaskite quartz and the pegmatites together simply because they roughly form by the same sort of felsic magmatism process. So let's take a look at these in a bit more detail. And essentially, like, of course, the most amount of detail is in the report, but to kind of focus in on these deposit types, most of the documented quartz resources in Queensland are of silica sands type, and they're all in far north Queensland and in Cape York Peninsula. And they're typically associated with quaternary sand dunes. So these operations are dry mining and sort of excavation type of deal, 10, 50 meters below surface. Now, what I find really interesting is that I think I forgot to mention it in previous slide. I'm going through it so fast. What I wanted to say is these are the important properties that we're after in the quartz crystal from which we can extract silica. So we want the silicon, high silicon content. These crystals actually have to be quite big, and they also, and because they're big, we also want them to be to remain coherent when they're being heated during that carbothermic reaction. So what I find particularly interesting is that silica sands are still economically viable type of deposit, even though there is no such thing as a centimeter large sand grain. Or if there is, I don't think I want to be at that beach. But that is to say, so the additional process in the production is agglomeration of these grain sizes, sort of grains of sand. Now, to sort of talk in terms of the mappable criteria. Sorry, I'm switching between screens here. So in terms of the mappable criteria, and the target areas, we identified 5 potential prospective areas. The source for these would be the quartz-rich protolith, typically sandstone, but quartz-rich igneous rocks are also possible. I guess for silica sands, because we're specifically after silica, we want to make sure that there is as little feldspar as possible. So we know that the documented occurrences are in a quaternary dune field complex. So the energy source is the recent wind-blown sediment deposition. During that process, there is sorting and winnowing. So that's how we end up without any feldspar or mica in these type of deposits. However, if they are still present, then they can be removed when already kind of excavated and then kind of just sifted. Here in Queensland, we're also dealing with prevailing wind. Westward direction is preferable. As you can see, the west side of Cape York Peninsula is peculiarly sand dune free. During the wind-blown transport, sand grains are reduced in size and naturally separated from impurity. So that kind of ties back to the like no feldspar or mica point. And like what we're suggesting in terms of target areas is really an extension from known occurrences and potentially next to extensive sediment-rich river systems. So this is target area number 4. There is a lot of there is a big sort of river system empties out into the ocean, and kind of brings in the sand sediments to the dunes, but then the wind kind of it's fascinating. But anyway, so this is the only probably area that is not really associated with any known occurrences or not very big occurrences, and same with target area number 5. Target area number 4 is also potentially not westwardly wind, But anyway, something to investigate. And then the second type of quartz deposits, so the granite-related alloskite type and hydrothermal quartz. So I'm recapping the composition and making and reinforcing the point that these have to be silica-rich. And in these systems, quartz recrystallizes to a higher purity variety during the hydrothermal alteration. So generally speaking, this type of deposit is preferable for silicon simply because it's low in trace elements. Of course, there is an exception to every rule, but if we're thinking about metalliferous systems that would form in kind of associated with granitic bodies, we kind of have to reverse our thinking and look for barren in terms of sulfides areas and as pure, so like free of any other elements as possible. The source for these type of deposits are the Luca granites and pegmatites and quartz veins themselves. The energy source, so it's all driven by the felsic igneous activity and the regional faults and shear zones. And here we map the regional basement terrains are of importance to kind of move these felsic igneous bodies. So the areas that we've identified as potential targets are in proximity to large-scale structures. And what's next? Depositional gradients. So different from, how you would think about a metalliferous deposit. What we're actually after here is the slow cooling rate. To make sure that the quartz crystals grow big. The bigger, the better in this case. And to summarize it, the target areas, the leucogradic granites and pegmatites near faults with evidence of fluid convection and zoning, so away from any metalliferous bodies, is probably the way to go. And I have one more slide, and this one is sort of, I titled it further work, but it's further work in terms of, society at large, because there are probably alternatives to silicon, particularly in solar powers. So some of the alternatives are to consider, alternative processes in this case is to consider a carbon-free process that wouldn't use med-grade coal or wood chips, charcoal, and for refining this silicon oxide. I know that there's some research happening in that kind of area. And then also researching possible alternative methods for making silicon itself. So the examples include supercooling liquid to form bulk amorphous silicon, or the opposite, a hydrothermal method for making porous silicon powder for optical applications, which would still result in a very high-grade pure silicon. For these processes and refining techniques, in theory, quartz of any size and purity can be used. So products like, quartz that is smaller in size, crystals that are less than 1 centimeter in size, or quartz that contains quite a few impurities. Remember that the requirement was that quartz itself had to be quite pure to begin with. So something like this, it would be quite handy because it would open up the possibilities of where to explore. And lastly, like at the moment, there isn't actually, like recycling of solar panels themselves is not a thing at the moment, sadly. It's not economically efficient. And so the silicon modules, the silicon cells themselves are not being recycled. or reused or recovered in any way. But the solar panels, and that goes back to the very first slide I showed, consist of a lot of layers, and it would be nice to come up with a way that would tap into any one of those layers. And at the moment, none of that is being done, or at least it's not economically efficient, because the cost of the mining product, the silicon out of mining product, is cheaper than recycling any of those parts. So there you go. I don't think I took a breath throughout the whole presentation, but that is the end.
Well, thank you, Katerina. It's really great to learn something about a part of our resources sector that I don't know a lot about. I mean, silica, that's just sand, isn't it? But
that's right.
No, that was really fantastic. And we do have a couple of questions for you. So as you point out, it's a pretty vital part of, our technology-driven future going forward. So what is the energy balance for the production of silica, and how much CO2 is produced? Is one question.
It's a very good question. I have to admit that I did not investigate that. So it kind of, I guess that was not the scope of work for this research. Simply, in fact, in a lot of reports, it would be omitted entirely that this is a big crucial step in the solar panel production. Like, you need coal to make solar panels. I think that's fascinating and a bit sad. I can't answer this question. I really don't know.
No, that's quite okay, because you're right. I mean, we set out to develop prospectivity models rather than answer the CO2 balance, but it is something that we as a group need to turn our minds to at some point. And it does, Katerina, lead into the next question from Graham Willett, which says, what potential then do you see for the development of new technology to extract and produce high purity silica in Queensland?
That's also a really good question. And well, from what I read and from what I understood, is it's really expensive here in Australia. So everything is being exported out to overseas, and I think startups in Australia would benefit from investigating things like this. So I guess biasedly, I think that there is potential, and how to implement it, I really don't know. I think it's more has to do with driving the cost down of like how expensive these processes are. But I think that there is great potential. And if Australia could lead in this area, then that would be great. That would put Australia on the map in terms of just technological advances like this. I don't think I'm answering the question, but yes, I don't think it's being done at the moment. It's simply because it's too expensive.
Yeah. That's the problem, I think, across a lot of industries. But got a lot of smart people working on it, so many brains are better than one.
Correct.
Thank you, Katerina. I really appreciate that. And there is a comment in the chat to say that that was really refreshing information. I agree. So thanks a lot. It's a really great presentation.